We now come to the three laws of motion. And so we look at the first law. Of motion. And this law says that in an inertial frame, the other two laws will also apply to inertial frames. Yes, in an inertial frame, if there is no force acting on it or no net force acting on it, so there may be forces more than one, but they all cancel out exactly. So there's no net external force acting on it. No net external force. I'll just see what we mean by external or internal. So if no net external force acts on it, so if the sum of the external force is 0, then the object will maintain its state of motion. Its state of motion. Which means that if the velocity was 0, it will stay 0. And if the velocity were constant at some value, it will stay constant at that same value. So the velocity does not change. And this means that it keeps going in a straight line with the same speed if it was going initially. Now, just going back here, in this case, when the velocity is constant, you read the ball here. Well, there are two forces acting on it. There's gravity pulling downwards and the surface is pushing it upwards. So the net force on it is 0, stays where it is. In this case, it moves, and that's because even though no force acting on it, but it starts to move, that's because it's not an inertial frame. This law doesn't apply there. This applies only for an inertial frame. Now, this law came about after experiments done by Galileo, who lived somewhat before Newton's time. And Galileo did some experiments. He took a plank and tilted it. And this is what we call an inclined plane. It's a plane surface that's tilted. And it's something very commonly used in a large number of physics experiments. And he put a ball or a cylinder on it at rest, and he found that it started moving down and accelerated. It's got faster and faster as it went lower. He also found that if the angle were, as we increase the angle of the incline, the acceleration increased. So the more the angle, the faster it goes down. That's sort of evident. Then he did another thing. He tilted the plane the other way, and from the surface, the ball was rolled, and it goes up. And as it goes up, it slows down and ultimately stops and comes back. So there's a negative acceleration. And again, if the angle is bigger, the negative acceleration gets bigger. So he concluded, when going down, you have positive acceleration. When going up, you have negative acceleration. So the question was, when it's horizontal and you roll a ball, it will not get faster because it's not rolling down. It should not get slower because it's not going up. So it should continue at a constant speed. Because here the V increased and here the V decreased, so here V should remain the same. But that's not what we see. And that's one of the things that Aristotle also said, that the state of rest is the natural state and everything will come to a stop. Well, now we know that's because of friction. So if you roll a ball on a rough surface, it's going to stop pretty soon. But if the surface is nice and smooth, the ball will go much further. So if we conclude that there's something on the surface that's slowing it down. So if the surface is sort of perfect, there's no friction at all, should continue forever. And that's what happens in space. We have the Earth going around the sun, and it's been doing that for billions of years, and should keep doing that for, well, indefinite period. So this is the first law of motion. Now we look at the second law. And the summary, briefly, it's F, again, sum of forces equals ma. So the sum of all the external forces on an object will create an acceleration a in a mass m. Now let's see how we get this law. So if you have a surface, let's say very nice smooth surface with very, very low friction or frictionless, and we have a mass m here, and it's at rest, so the speed is 0. If you apply a force to it and start pushing it, it's going to start moving to the right. So if this is like a table in the room, and it's just going to stay there unless a force acts on it, which is the first law of Newton. But if you start pushing it from one side, well, it's going to start moving, and it's going to come somewhere else. So because the speed was 0, and because now it's moving in this part, it must have some velocity, and so the delta v, there must be some change in velocity over, it took some time. So that is the acceleration, which means that when you applied the force, you created an acceleration. Now, if you apply a small force, you will have a small acceleration. If you apply a big force, you'll have a big acceleration. And we can think about that in terms of if you're in a car and you have your engine here, you apply the accelerator and you don't press it very much. So the car initially, let's say, was stationary, the car starts to move and gets faster. But you didn't press the accelerator very much, so you accelerate slowly. But then there's another car near you, which is like, for example, a sports car, and with a strong, powerful engine. Initially, it was also stationary, but he pressed the accelerator a lot, and then very soon that car accelerates and goes far ahead of you very rapidly. So here, because you press the accelerator a lot, you have a large force and you have a large acceleration. And so we can say that the acceleration is proportional to the force. The bigger the force applied, the more rapidly the car will get faster, or the more bigger is the acceleration. Now, so we have one equation, not an equation, but we have one relationship. Now let's suppose you take this very powerful engine and put it in a truck, okay, and you accelerate, press the accelerator. Well, the truck is not going to accelerate very much. It's going to accelerate very, very slowly. And that's because even though the force is still the same in this case and this case, but here the mass is much bigger. And so we see that as the mass is much larger, the acceleration is much smaller. And so the acceleration is proportional to 1 over m. Now, with these two relationships, we can conclude that the acceleration is proportional to F over m. And we find that the constant of proportionality is 1, and therefore the A becomes equal to F over m, which is rearranged to write as F equals ma. Now, we make a small change here. Since the force is a vector, we can do that. And also, there may be more than one force acting on it. You may have you have the engine pulling forward, you have the friction in the wheels, you have the air resistance pushing backwards. You have a number of forces that will result in the acceleration. And so, a proper or more better equation would be to add the summation sign. So these are, so this is the sum of all external forces leads to an acceleration equal, given by this equation. Now, what we mean by external force? Well, if you have a bus and you have a number of seats here and people are sitting on it, okay, and the bus engine has a problem, and so the driver says, okay, everybody start pushing the bus. So this guy pushes the front seat, and this guy pushes its front seat, this guy pushes this front seat. Everyone pushes on the front seat. The bus will not start to move. It will move only when they go out and start pushing over here. So then the bus will move, because now it's an external force. When they're pushing from within the bus, these are internal forces. Internal forces do not change the state of motion of an object. That's because when he pushes this way, well, his back has to push the seat backwards, and the two forces are equal and opposite, and the net force becomes zero. So that's what we mean by when we say all external forces. So this is an external force, and these are all internal forces, and we don't use those. Now, a useful modification of this equation which we'll be using is that this force, because it's a vector, or let's just say it says one force, it will have xi plus fyj, and we may have a third component k, even though we will normally just be concerned with x and y components. And the acceleration is also a vector, so we will have axi plus ayj plus azk. And now we write them over here. We have fxi plus fyj plus fzk equals m axi m ayj. We can multiply the m with each of these terms, plus m azk. Now, the I can only compare with an I, and the J can only compare with a J. And so we can say that, well, again, we can add the summation sign over here. So we can say that the sum of all the forces in the x direction create an acceleration in the x direction times m. The sum of all forces in the y direction create an acceleration in the y direction, and the sum of all forces in the z direction create an acceleration in the z direction. And we will use these three components to solve our problems. Okay, so now we come to the third law,